All right, folks, so let's start. This is Dr. Yuzo, ECE 341 Power System class. Today is our 14th lecture, and can you guys hear me? And also being able to watch my shared screen.
Yep.
All right. Thank you, folks. Thank you. All right, let's go ahead. First of all, obviously, we are reviewing the formulas we learned from last lecture regarding the power flow. And pretty much we are assuming bring up a kind of network per phase representation of a network. What you're seeing here is a bunch of buses. First bus, we call it I, and then a connected to another bus, we call it J, and the bus K and L. So up to 4 buses in this network. And you are also seeing the connection between I and J, one connection. We call this as line, one line in between. Another line between I and K, another line between I and J, I and L. So in this network, as an example, we are able to see many powers. Many powers. First power we can see is from bus I towards bus J. You have a apparent power S sub ij. Okay. This is from I towards J. And remember, the power flow appears in pairs. So this line here, line flow appear in pairs. So along the same line, we have one direction Sij, we will also have another direction Sji. Okay. So along the same line, you have 2 line flows. And they shouldn't be same. Okay. Because in the middle, we have what? Plus. Okay. Line flow and line loss. Same thing for other lines. Besides, we also learned the bus power. What does bus power means? Bus power means, for example, to this bus I, what is the total power of bus I? It's obviously equals to the sum of the other side of the bus I, which is Sij, Sik, and Sil. So summing up all of the power leaving the bus I. So line flows, line loss, and the bus power. And repeating the formulas here, we are having first line flows, how we calculate it, Si equals to voltage times the current conjugate. As simple as this. Once again, this is per phase representation, so we are using V times I. 3-phase system, you don't forget to times 3. But generally speaking, we just talk and study about the per phase network. And I equals what? I equals to, be very careful. We're talking about from I towards J. So both power and current have direction. Right? So the current is from I to J voltage potential difference. Either times the admittance in between or divided by the impedance in between. Right? This is how you got the current. And also don't forget the conjugate out here. The other way around, so from bus J towards bus I along the same line equals to the Vj, this time is Vj, times the current from J towards I, so Vj minus Vi. Once again, times the exactly same admittance, or divided by the exactly same impedance. This is how you got the current. Line loss equals to very easy. You sum up the 2 line flows along the same line, Sij plus Sji. bus power just sum up all of the Sij, j from 1 to n. Okay, and just up to how many lines, how many other buses connected to the bus I. Okay. These are the formulas we need to apply. These are the formulas we need to apply. Nothing new at all. Okay? Because this is nothing but v times I conjugate. We have back in module 2. So based on which we can do a example. Okay. A little bit time consuming, but be patient. Do a little by little, step by step. And then the rest of the time today, we're gonna review the midterm 1. Okay. Example. A 3 buses network. 3 bus network. So what does this mean? This means a generator. It means generator. So this bus is what? Is a source. Source bus. That's okay. Now the formula remains same. The formula remains same. This is a bus 1. And the key is bus 1 has a bus 1 voltage as 1.05 angle 0 per unit. The given network gonna everything, every quantity are in per unit. Okay. Per unit. And then this is V2. V2 equals to what? V2 equals to well, I'm sorry for this tricky number, but if you recall, these bus voltages are obtained from iterative methods. That's why the number is not nice number at all. No. Okay. Bus 3 with voltage of 1.001, 25, negative 2.86, 24 degree per unit. And the connection is like this. 3 buses with bus voltages given. And just find line flows, line loss, and bus power. So all of them are plural. Let's see how to do this. Oh, one is missing. One very important thing is missing. Anyone can tell what is missing? The given information. It's very important. Without it, we can't do anything, actually.
Don't we need to know what word subscripts for the buses are, or no? Are we just
subscript? Well, this is bus 1. This is bus 2. The subscripts are given. Yeah.
The base.
Base value, very nice. The base value. Well, I'm sorry, but base value is actually not the most important thing I meant. But base values are needed. Base values are generally given. For example, this one is given as 100 mega VA. And what else we need? We really need it. Actually, good. Anil got it. Anil got it. What is it? We don't have this. Okay, we don't have it. Then we can't do anything. Obviously, 3 lines, we need 3 line impedance, all right, or admittances, whatever. Good job on you. And Z12 is equals to unit. Everything per unit. And to the last power. Okay. That's what the given base power for. You see. 13.0 plus 8.03 unit. Just calm down and be patient to copy the right problem. Otherwise, good. Before starting to solve it, okay, let's go back to here. I forgot one thing. It will be very, very helpful if at the beginning of the problem solving, you are kind of aware how many results you need. How many? I mean the number of them. But first of all, let's talk how many line flow we need to calculate given the network.
Well, isn't there 3, but are you also including the fact that the power could flow negative and basically the opposite direction of that? So would we consider it 6 or 3?
Well, pair, like I said, in pair. So the generic or generalized sum the number, how to summarize it? Line flow, how many? Up to what, we're saying? We're trying to generalize a,
right?
What is it?
Up to 6.
For this particular example 1, yes. But generalized line flow, how many?
Wouldn't it be 2 multiplied by however many lines are in the bus?
No, very good, very good, very good. Number is equals to 2 times number of lines. Okay. How many you need to solve? It's obviously very helpful if you know the number at the first place so that you won't miss any. You need to count how many. How many line flow you need to calculate. Why John got 6? Because you have 3 lines. 1, 2, 3. Be careful. We're not talking about bus. We're talking about lines. How many lines? 1, 2, 3. 3 by 2 equals to 6. Second, how many line loss you need? The number of it equals what? This is very easy, right? How many line loss you need?
Number of lines.
Exactly. Number of lines, right? It's just how many lines you have. And at last, how many bus power you need? This is also easy enough, isn't it? Number of what? Buses.
So for the line, do we actually assume that if, let's say there's 3 lines on the bus?
3 lines on the bus, and then what?
Do we assume that when they're only giving us 1 impedance from that direction on the bus, we assume all 3 lines are the same impedance?
No. That's why we have the subscript as index of the bus. The subscript here, 1, 2, 3 here, they are referring to what? The bus. So 1, 2 means what? The impedance between bus 1 and 2, which is the line here. 1,
Yeah.
3 means the impedance between bus 1 and 3.
But if say for example Z12 had 3 lines, is that
You mean
Z1?
3 faces?
Yeah. Is that
3 faces, yes. 3 faces balanced.
so? We have to assume then that those lines are the exact same as Z12, right?
You mean 3 among 3 faces lines, right?
Yeah, both 3 faces.
Yes, yes.
are the same.
Balanced. As once again, balanced. Yeah, we are studying a balanced system. Yeah. All right. So according to this rule, go back to this example. We know we are going to calculate up to 6. So where are they then? Also, it's also helpful to figure out where are they. This guy is what? Sij, right? Which is what? S12 specifically. What is this? S13. 2 out of 6. Where are the next 4? Here. What is this guy? That's 2, 1, right? What is this guy? 2, 3. 2 left. Here is what? 3, 1. Here is what? 3, 2. Making sense? Up to 6 line flows. Up to 6 line flows. The line loss were where? Here. Loss 1, 2. Here was loss 1, 3. Here is loss 2, 3. Does it make sense? Six line flows, 3 line losses, all make sense. And at loss, we have what? 3 buses, so 3 bus power. 3 bus power, where are they? Here. S1, right? S2, S3. Making sense? I mean, the location, the rough location. If you see how to specifically label the power into the graph, because we need to do that. Okay, we need to find and label. Find and label. Okay. We need to label them into the power graph. All right, if these clear, then we can go ahead. To find the. I think we together do 1, maybe 2, and then leaving the rest of the calculation to you guys to exercise. And according to the experience, it's not very easy to do them all right. Okay, it's every single power right. Seems not easy. All right, let's begin with S12 then. S12. S12 is power here. Obviously, according to the formula, what do we have? V1, right, times numerator is V1 minus V2. Divide by Z12 and then conjugate. Does it make sense? It's not difficult at all. And everybody knows how to do this. However, not everybody can get the correct answer here. And we start to substitute the given numbers. So 1.05 per unit times it's 1.05 minus 0.9883 angle of negative 3.50. 5 degree. divided by 0.02 plus J 0.04. Nothing difficult, nothing difficult. And go ahead, equals to the voltage 1.05 times the current. Current conjugated force. To be 1.9 minus 0.8 J conjugate. And equals to basically 1.995 plus 0.84 J. Be very careful. The unit for now is what? Per unit. Okay, the unit is per unit. Unit is per unit. And what we need next to do is convert it to the SI unit by what? You need to recall the per unit value times the base value equals what? Actual value, right? So this per unit value times the base value, which is 100 mega VA. Then you got 199.5 plus 84J mega VA. Because the base power is 100 mega VA. And meantime, you're very clear that this is what? P. 1, 2. This is what? Q. 1, 2. It matters because later on we will see we can label the active and the reactive power separately. Okay. We're not labeling a single S. We're labeling P and Q separately. Any questions? It's super easy, isn't it? Look like so. Okay, look so. When you do it, but not necessarily. I think that's all I need to teach. If no questions, then go ahead for rest of the 5 line flows. Yeah, the workload is a little bit high, but calm down and do it as exercise. Extremely helpful towards your later exam. Okay. Don't count on your after class time, okay? Because most of the time after the class, you won't have time for this class anymore. You know that better than I do. So go ahead. Give you guys just line flows. The rest of 5 line flows. I'll give you guys maybe 10 to 15 minutes. And really do it. Really do it. Okay. Go ahead. Can you guys hear me now?
Yeah.
All right. So here are the solutions basically. Anyone can confirm these results up to 6 line flows? Any troubles, any problems?
I got the same answer.
Good. Great. Did I ever got them? Kevin saying my 2332 are different. How much different?
A lot. I have negative 204 and a positive 209 megavolt amps. I'm off by a lot. So I'm thinking
That's too much. That's too much. Definitely wrong. 2332. How about others? Any anyone got any input? Eamon got the S21 wrong. Well, okay. Any other comments? Because the rest of the works are very straightforward, right? You sum each pair up, you end up with 3 line laws. And then 3 bus power is also a very simple algebra.
V3 again. Maybe I wrote it down wrong.
V3.
Yeah.
You see it?
Yep. I'm getting the same values that I got the first time.
So you don't have any issue of copying the wrong voltage?
No.
How about others? Are you besides of Yadav? How about others? Any confirmation? Anyone else?
So do you require us to express them in actual, or can we leave them in per unit?
You need to convert them to the actual.
Oh, okay.
Yeah, that's what is given base power for. Anyways, how about your results for S23 and 32?
I got that. I'm just multiplying most of them out right now for the actual.
I mean, my point, are you confirming my results or receiving the same as Kevin? Or any other different
yeah, I
values?
got the same.
Okay. All right, thank you, Sawyer.
I found it. I hit my decimal too early in my angle for V3.
All right. And then we can save this. I think it's just patiently typing the numbers, and then yes, it's a little bit tedious, but my suggestion is, once again, when you do the operation, you probably want to break down this operation into 2 steps. First, maybe find the current first, and then use the conjugate of it times onto the voltage. I think that's my only I think help can provide. Other than that, 3 losses we just talked about. Very straightforward. Right? Be very careful. It's a plus. Okay, it's a plus. You can imagine. It's not surprised that 1, 2 are 1 S1, 2 is positive, positive. 2, 1 is negative, negative. It makes perfect sense. Because the power is one way. You're not having both way power. That doesn't make any sense. So you sum them up, and then the resulted loss equals to 8.5 plus 17J mega V8 plus 2.3 equals to 0.8 plus 1.6 J mega V8, and then the last one is 5 plus 15J mega V8. And these are the power loss. That's straightforward, and then the rest of the thing is the bus power. Bus power. Just once again, be patient. Be patient, and then your S1 equals to what? Oh, S1 equals to what? By the way, by observing the network, S1 in this example equals to what? Anyone knows? Anyone knows what is the S1? Because
S12 plus S13.
a good 1, 2 plus S1, 3. There we go. Okay, no, is right. 2 is what? S2 equals what? 2, 1 plus 2, 3, right? The first subscript is the bus we are looking power for, right? Same thing here. 3, 4, 3, 3, 4, 3, 1, sorry, 3 and 3, 2, right? Eventually, what do you got? 1, 1. V8 S2 equals to 2, 3, 2, 1. There might be a little bit off in the digits because we are calculating big power. The bus voltages are quite tricky. That's fine, but roughly it should be like this. It should be like this. These are the line losses and bus power. Here, Neil is asking, can we label the SL32 instead of SL23? Yes, you can. Okay, line loss is something stay in the middle of the line. It's actually, it doesn't matter which way. It doesn't matter which way. This is the loss. Right. And if these are fine, we can go ahead to do so-called plot, right? Remember, the problem also asking you to label. So how to label all of these into the per phase network. And this is something we need to be careful too. How we label is like this. First of all, repeating the given network, given network. And then first we label S12, right? S12 is here, S12 is here, S12 is here. So how we label it, first of all, we are labeling the SI value, not per unit value. Second, we are separating active and reactive power. Therefore, how to label this? One power along the line, one is active and the other is reactive. So we label them on two different sides of the line. What I mean is this. So we're seeing S12, the P12 is 199.5, right? It's positive. We know it's towards this direction, no problem. The value is 189.5. Active power, we are using a line with arrow on it, representing the active power. The other side of the line, we are labeling, because it's a positive 84. Positive 84. However, in this way, we are not able to tell which is which, right? Which is active, which is reactive, we cannot tell. So we need to use a bar across the line to represent, or say to differentiate the reactive power from the active power. So above the line, it is active power without bar. Below it is the reactive power with the bar. I'm labeling the magnitude only without J. This is S12. S21 similar. S21 is over here, this value, right? That's S21. S21, it makes perfect sense. It's supposed to be S21 from 2 towards 1, right? However, look at the value, it's negative value. So what do? We flip the direction of the arrow and label the positive value. Does it make sense? We flip the direction and also we flip the sign. So, okay. Above the line, once again, is active. 199. Below it is bar, label 67. Make perfect sense, right? You're sending 199.5 towards 2. How much is received? 191. The bus 2 is not receiving all of the active power sent by bus 1. Why is that? First, perfect sense. There's line loss in the middle. Line loss we calculated as 8.5. Does it make sense? Below the line is the reactive power loss, 17. Perfect sense, right? Perfect sense. Give you guys 5 minutes to do the rest, label the rest. Oh, of course, now let me finish one. This is a 2 line flows and 1 line loss. I need to give you an example how to label the bus power. Bus power S1 here, this guy. It's 409.5 positive and plus 189J. Positive means what? Means the power is going into the bus, active and reactive. Obviously, you need to differentiate them. Active given the 409.5, reactive is 189. Right? The power given to this bus 1, and it is assigning it to other buses. This is a positive and the positive. Again, 5 minutes. Go ahead. Label all of the rest. All right, let's see the solution here. So basically, the next S13, S13 should be here. Okay. Starting from bus 1 towards bus 3. So according to the result here, 1, 3 is positive and positive. A positive 210 and positive 105 as reactive power. 3, 1 is negative and negative. So here, be very careful, okay? This is a vertical line, right? So you're labeling active or reactive on which side. It actually does not matter. Actually, it doesn't matter for the horizontal line either. However, the key point is you need to make it consistent between the S12 and S21. Between S13 and S31. Look at the active power. Active power is above the line, right? And to here is supposed to be right of the line rather than the left of the line. Does this make sense? This is the bottom line you need to keep. Which side is actually doesn't matter because you have power here to differentiate which is active, which is reactive power. However, you need to keep the active power on one side of the line. Keep the reactive power at the other. All right, this is how you decide which side is which. And this is a 3, 1. A 3, 1, you have negative 205 and a 90. Similarly, you have 2, 3. 2, 3. Where's 2, 3? 2, 3 is here, and say is negative. So you need to be very careful. So you can realize that between 2 and 3, who is sending power to whom? It's bus 3 or bus 2, actually. Okay. So it's negative 65.6 and 33.2. And here it needs to be what? The right-hand side now becomes the reactive power to be consistent with here. Okay. Reactive power now is 32. 32 is 44.8. Active 66.4. Power loss in between must follow the same size rule as well, right? So to here, this is the active. This is active 5. This is a reactive of 15. Here, this side is reactive, which is 1.6. This is the active 0.8. Line flows and line losses, done. And then loss power. S2 here, negative. Negative means what? Negative means leaving. Towards right. Active is 256.6.2. S3, same thing. As active 138.6, reactive 55.2. And of course, it makes perfect sense that if you calculate what? This guy plus this guy equals to this guy. This guy plus this guy equals to this guy. Perfect sense, right? Perfect sense. You don't have any loss or losing at this bus because it's a node. It's not taking anything. So this side of the bus is equals to this side of the bus. Perfect sense. Same thing for these two buses too. Any questions regarding this example?
So it's required that the complex arrows all be on a specific side for when you're labeling your line, right?
But once again, which side, it doesn't matter, but you need to make it consistent. Above the line, active, active, okay. Below it, reactive and reactive. Same thing here. Above it is active, and then you turn the 90 degree, and then the right-hand side is supposed to be active. Make it consistent. Along one side of the line is active and always active.
So when V3 is supplying 44.8, and then obviously this is in mega, but
Yes.
so would we say that it's supplying, well, it has to supply some sort of positive reactance, right? Or the power is passing some sort of positive reactance, right?
Yes.
And so
Reactive power, yes. So
that is that the main goal to kind of see that, like when we're analyzing the power flow, is it to look at the inductive like loads or to see how the power, because I get where, you know, obviously the non-reactive power, the active power, but what necessarily per se does it mean when you have 44.8 mega volt amperes being supplied to the bus from V3 to V2? Like what?
like what? What's the sense? Or
That V2 is more inductive, and thus why the V2 node is 110.2 away. Because if it's out, does that mean that it's inductive, and in means it's capacitive?
the here 110.2 here is a negative power. It's going to this direction, which
So
means assuming here's a load here, this load is what? The receiving this amount of power, or say the delivering reactive power.
it's
Delivering
negative.
negative reactive power means is capacitive or inductive. This is something you can check back to module 2.
Whereas the 44.8 from V3 to V2, that's supplying inductive reactive power, right? Yeah, it looks like it. From 3 to 2 is 44.8 J positive. So it's just kind of weird, I guess. From looking in the nodes perspective, it seems like when you sum all of them up, it's kind of like opposite. I don't know if that makes much sense. From each other. Okay. I don't think we can hear you, Dr. Zoe.
I cannot hear him either.
Yeah, we lost audio.
Can you hear me now?
Yeah.
All right. What I'm saying is that how you do this is just basically the load. This is the source. These two are load. Load might be a capacitive or inductive. Of course, the resultant reactive power could be positive, could be negative. However, since this is a load, this should receive the active power. Right? It doesn't make any sense if you're providing any active power. As to reactive power, well, it's up to is capacitive or inductive. That makes sense too. But this is the statistics of the exam. I again break the grade down to different level, so you can tell which level you're at. And be careful, the grade here is referred to the grade posted in the grade book in Canvas. rather than the grade on your exam paper, because the grade on the exam paper is 1 or 2 points less than the gradebook grade. Everybody notice that?
Yeah.
And but does anyone know why? Why you're receiving 3 points, 1 or 2?
Oh, wasn't it like way back before we even took the test? I don't know if it was 2 or somebody had talked about we corrected that issue with the phase, the symmetrical components.
Here we go. John got it. By checking the recorded lecture, I think you guys can recall back the symmetrical components example. I gave the example, the numbers backwards. I gave the wrong numbers. I remember it was Johnson, the first one bring it up, asked me to repeat the details. And afterwards, Kevin, Noah, and Sawyer confirmed that is you guys not getting the same answer as I presented. And then I checked, waste kind of 10 minutes, I think. And besides of apology, I promised to give you guys some points in the exam. And here we are. Okay. I provide a review. You follow the review. Exactly. Okay. To those reviews, I'm mentioning this certain kind of a problem, how you prepare. You prepare according to the example in the lecture. You have recorded lectures. You won't miss anything. So are you treating the online course in the same way you would do in the regular in-person class? This is absolutely determining how well you're going to do in the exam. Okay, as from your end, first of all, I'm sorry, I'm not trying to blame anyone. I'm telling the truth. Okay. So if you are performing not very well this time, you need to think, or say at least ask yourself this question. Have you done everything you would do in the regular in-person class? If the answer is no, because you don't need to answer to me, okay? You need to answer this to yourself so that you know what to do in future. Because the standard of the grading won't be changed. It's an online course, so I give you some free points. No, I cannot do that. Okay, I cannot do that. Okay. Standard remains same. Okay. You have to do something. If you have questions, of course, feel free to ask. You have plenty of opportunity to do that. Okay. And I don't think I gave any reason for you to feel uncomfortable either. So ask questions and do your job. Okay. Really study it. And if you think you missed anything, remember we have recorded lectures. You shouldn't miss anything. There's no way for you to miss as long as you are willing to know. And of course, it's 40% of the class is beyond A minus or beyond A minus, and then it's very indicating that, well, as long as you follow, it's not that hard. I don't think so. I'm not giving extremely hard time for the exam. No. Okay, this is the first of all, the attitude. Okay, if you're doing like this guy here, of course, keep doing what you have been doing. I mean, hands down. Okay, but if not, or you're not feeling satisfying with your grade as well, then you know what to do. Okay, because there are a couple of students even copying the history problem solutions which have completely different given values, given numbers, as the solution of the exam problem here. Okay, that's ridiculous. That's really ridiculous. So if you don't agree with this comments, feedback, or you have some thoughts, feel free to let me know. We can talk. Okay. And besides of this, and then let's see the problem. What problem we had? Yeah. Not much time, but at least we probably can finish one problem, leave the rest of 3 to next lecture. We still have time. The first problem, if you did very well in the quiz, you shouldn't have a big problem here at all. However, if you use the check for the quiz and didn't learn anything from that check solution, you're gonna of course have a big trouble here. Well, Gavin is asking, where can I find my grade before the points were added? I have returned the graded exam to you guys, right? Everybody receive it?
Yeah, I think you have that written on there too, right? Like whatever you've added additional.
No, I'm not writing down the additional points on the paper. No, I'm not. You are seeing your real exam grade on the paper, and the first page, right upper corner. That's your real grade. And after given 3 points, either 1 or 2, you're gonna see your grade, new grade in the grade book in Canvas here. Okay. By clicking here, you see my cursor here, and you're seeing your grade with 3 points. The new grade there.
And did you email us the grade without the added points?
No, and once again, Gavin, I have returned the graded exam in Canvas. I didn't email anyone except you submitted the exam by email.
Okay, gotcha. I was just I guess I was just confused. Thank you.
Mm-hmm. You should be able to see there, and which obviously these are 2 different grades. Someone, well, by the way, why someone received 2, someone received 1 only? Anyone knows this? But this is something I do for those who actively engage the class. Because once again, we have recorded lectures. So from that recorded lecture, everybody can easily know who engaged in that discussion, right? I mean, who brought up the issue, who gave me the feedback telling me, no, I'm not getting the solution you provided. So everyone can tell, engage in that discussion. That's why those guys receive 2 points, and the rest of the guys receiving 1. That's how I manage it. Okay. Everything has reason, okay? Just like my exam. Back to here, listen up. I think this circuit, the only thing I want to emphasize is R3, L2, after you have their impedances, this branch is parallel with R2, L1, R4, C1. These are 2 branches parallel. After these 2 branches parallel, the total is series connected with R1. This is the connection of the circuit. If you understand this, you won't be off by too much. And besides, of course, be very careful reading the problem. Is asking for the power for R4 and C1. To make it clear, I use the dash line box to combine it. Can you see that? I'm reminding you guys that don't mess up the question. I'm asking for here and particularly here, not anywhere else. Okay, so you are looking for the power for these 2 guys and these 2 guys only. So what can you do? you can use a 1 voltage divider to find the voltage across R3 and L2. And this voltage, you use second voltage divider to find voltage across R4 and C1. Or you can find, many of you guys find the current through this branch by a current divider. That works too, of course. Okay. So you have voltage or current. You don't have to have both because you know the impedance easily, right? You use the conversion impedance times the current magnitude square, or the voltage magnitude square divided by impedance conjugate. Either formula should work. Either formula should work. Okay, so you can find the power up here. Quiz 1, only difference is the quiz 1 problem. The only difference is the connection. Connection. Idea remains same. And also here we are not taking care of any power factor correction. So this is the problem 1, and leave the rest of three problems, especially number 2. Number 2 need to be well. Once again, lecture 6. Okay, lecture 6 is the lecture you want to go back to review the example over there to better understand the problem 2. Since our very last exam will cover that knowledge once again. Okay, that's for sure. Okay, thank you for attending today's lecture, and we're gonna continue our review by Wednesday. Okay, all right. Thank you. Bye.